Section 15.5, Arithmetic Series. Before I continue talking about series, let me first discuss the sequence of partial sums. Okay. So first let an be some sequence. Then we will define the sequence of partial sums as follows. You'll let S sub n, S sub 1 equal A sub 1, and you'll let S sub n plus 1 equal S sub n plus A sub n plus 1. And this is for all natural numbers n. Okay. And so that defines a sequence of partial sums. So suppose we have the following sequence. Then the sequence of partial sums would be 1, 1 plus 3, 1 plus 3 plus 8, 1 plus 3 plus 8 plus 7, 19. Okay, so we can think of this as just 1 plus 3 plus 8 plus 7. I'll give you a notation, the sigma notation. And so the capital Greek letter sigma just means to, well, this is called the summation symbol. And that this just means to add. Okay. And so from the above notation, we will use the sigma notation. So rather than, so let's say k equals 1 to n of a sub k, that's just the nth term of that partial sum sequence. So this means that the sum k equaling 1 to n of a sub k is just a1 plus a2 plus a3, a sub n. Okay. So this is your dummy index. This is your lower limit. This is your upper limit. And this is your summation symbol. Okay. So let's do some examples. On page 664. Let's do problem number 1. Summation n equals 1 to 10 to n. In exercises 1 through 12, write the series in expanded form. So this is just 2 times 1 plus 2 times 2. So the first thing we do is I replace this dummy index by the lower limit. Then add, put the next natural number into the formula, keep adding until I get to this upper limit. And so I'll replace n by 3, 4, 5, 6, 7, 8, 9, 10. And that is your answer. Let me do problem number 3. Sum n equaling 1 to 6 of 4 minus 3n. So let's replace n by 1, replace n by 2, replace n by 3, replace n by 4, replace n by 5, replace n by 6. Since the upper limit is 6, then I am done. Five. Sum n equaling 1 to 7 n squared plus 1. Replace n by 1, 2, 3, 4, 5, 6, and finally by 7. Problem number 7. Sum n equals 1 to 8, 3 times 2 to the n minus 1. So this is equal to 3 times 2 to the 1 minus 1, since the lower index is 1, plus 3, so replace n by 2, the 2 minus 1, plus 3 times 2 to the 3 minus 1, plus 3 times 2 to the 4 minus 1, plus 3 times 2 to the 5 minus 1, 6 minus 1, 7 minus 1, 8 minus 1. And so since the upper limit was 8, we are done. Nine, summation, n equal 1 to 7, 5 times negative 3 to the n minus 1. Replace n by 1, 2, 3, 4, 5, 6, 7, and you're done. Eleven, sum k equaling 1 to 5 of negative 1 through the k minus 1 power times 1 minus k squared. So this is equal to, replace k by 1, by 2, by 3, by 4, by 5, and that is your sum. 13. 2 plus 5 plus 8 plus 11 plus, and keep going. And we want to have 35 terms. In exercises 13 through 18, write the series in sigma notation. Okay, so the first thing I have to do is I have to discover the underlying sequence. And so if I look here, I have 2, 5, 8, 11. So this looks like an arithmetic sequence. Because you keep adding 3. And so that means that since this is an arithmetic sequence, then the series formed from this arithmetic sequence is called a arithmetic series. And so that's the title of this section, arithmetic series, which is just a series that is determined from arithmetic sequence. And so I know the general term for arithmetic sequence, a sub n, is equal to a sub 1 plus n minus 1 d. And so a sub n is equal to the first term, 2, plus n minus 1 times a common difference. Well, I see I'm always adding 3, so 3. Let me multiply 3 inside the parentheses. And so I get a sub n is equal to 2 plus 3n minus 3. So a sub n is equal to 3n minus 1. Okay, so now I can write this series from above as the sum. Well, there are some choices here. And actually, one of the things you notice is that I said that we had a dummy index. The fact that we have a dummy, the reason it's called a dummy index is if you look up here in this series, say like here, the index, dummy index was k, but the result had no k's in it. You can see that, well, obviously the first term was 1 because that's where you started, and the last term was 5 because that's where you ended. But there was really no index in here, k. It just was part of the notation. So that's why we call it a dummy index. I could have called this, rather than n, I could call this k. So let me write this in terms of k. So I'll say that the above series is just the sum and I have some of, I'll call the index k. I've got a choice of where I want to start. Since, well, actually, in this case, I don't have a, I'll say that I would normally have a choice where I would want to start this summation. But in this case, I actually have no choice because in order to use this above formula, I've assumed that we start counting when k is 1. So there's really no choice here. K must, the lower index must be 1. And once we do that, then I know that the upper index is the number of terms. And so that's the way we wrote it. And, well, a sub k is 3k minus 1. And that is your answer. So notice that if you plug in k equal 1, you get 3 minus 1, 2. Then you add, plug in 2, you get 6 minus 1, 5. So it's 2 plus 5. Plug in 3, 9 minus 1 is 8. So 2 plus 5 plus 8. Plug in 4, 12 minus 1 is 11. 2 plus 5 plus 8 plus 11. You get the above series by just plugging in these values for k. And well, it says to add up the first 35 terms, which you did. Okay, let me do problem number 15. Negative 5 plus 5 plus negative 5 plus 5 plus negative 5. And you do this, and we want 20 terms. Well, I want to figure out what each of these are. Well, that's pretty easy. And maybe I'll call this subscript a sub k. I'll use the dummy index k. Well, it's going to be always equal to 5, but it either will be plus or minus. So I'll put minus 1 to the k times 5. So you notice when k is 1, I get negative 5. K is 2, I get positive 5. K is 3, negative 5. So it keeps alternating like what I've written here. This actually turns, and so this is this alternating series. And so my sum should look like the sum k equaling 1 to 20 of negative 1 to the k times 5. And that gives me my answer. Let me do problem 17. Three, 1/3, 1/9 plus 1 over 243. So here they don't tell you how many terms. Okay, so I have to figure out what a sub k is. Well, it turns out in this case, it looks like a geometric sequence, just like this was a geometric sequence here. And I had a resulting geometric series. And so this looks like a geometric sequence. And well, the first term was 3. And I kept multiplying by 1/3. Okay. And so if you plug in 1, you get 1/3 is 0, which is 1 times 3 is 3. Plug in 2. 3 times 1/3 is 1. Plug in 3. Well, 3 times 1/3 squared, 1/9 is 1/3, etc. So now the only thing is I have to figure out, well, in this case, what is 1 over 243? What is the value k? So that this formula here gives you 1 over 243. Well, let's plug in and let's see. Let me divide both sides of my equation by 3. So you get 1 over 712. Oops. So multiply by 3, that's 729. 12. So 729 is equal to 1 over 3, the k minus 1. Well, $721 is just 3 to the 9th. Let me check. 3 times 3, 9 times 3, 27 times 3, 81. Times 3, 243 times to the 6. 3 to the 6. Sorry about that. Is 729. Okay. Therefore, since the exponential function is injective for non-zero bases and bases that are not 1, and since the exponents are the same, then since the bases are the same, then the exponents must be the same. And so that says that k is equal to 7. And so my above series can be written as 3 k equal 1 to 7 of 3 times 1/3 to the k minus 1. And that will give you the above series. Okay. You could have actually made some different adjustments on how you wrote this, and you would have gotten equivalent correct answers that could look somewhat different than what I've written. 19. So again, let me just spell this out. Arithmetic series. An arithmetic series is a series derived from arithmetic sequence. Okay, so let's do on page 664. Problem number 19. -2 plus 1 plus 4, 7 plus 10 plus 28. Okay. Plus a whole bunch of other terms coming up to 28. So the question in exercises 19 through 24, identify whether the series is arithmetic or not. Okay, so in this case, I notice that the underlying sequence, -2, 1, 4, 7, 10, etc., is arithmetic because I'm always adding 3. -2 plus 3, 1, plus 3, 4, plus 3, 10, plus 3, 13, 16, 19, 22, 25, 28. Okay, so each term here is found by adding a common difference, 3. Therefore, this is an arithmetic sequence, and once I add them up, this is an arithmetic series. So yes, this is an arithmetic series. (21) 1/2 plus negative 1/2 plus 1/2 plus negative 1/2, etc. Well, I'm not always adding the same amount to get the next term. 1/2 minus 1 is negative 1/2. Minus 1 is negative 3/2, not 1/2. I'm always multiplying by the same number. So it turns out to be, so no, this is not arithmetic. So no, it's not arithmetic. It actually turns out to be what's called a geometric series because I keep multiplying by the same amount, negative 1. So this is a geometric series. 23. 1 plus 9 plus 25 plus 49 plus 81 plus etc. Again, this is not an arithmetic series because 1 plus 8 is 9 plus 8 is 17, so that doesn't work. So no, this is not an arithmetic series. It is, well, what's called a Riemann zeta function. And so this is, 1 plus, it's 1 squared plus 2 squared plus 3 squared, etc. And it turns out that this is a millennial prize. So one of these problems from the Clay Institute is to show, well, to prove the Riemann hypothesis. That the only non-trivial zeros of the of this function. Lie on the line. Well, lie on a line. Where the an imaginary part uh, of those roots are negative 1/2. Okay. Oh, uh, and they'll give you, this is $1 million prize. $1 million to solve it. But of course, it's a hard problem. Okay. So let's look at a formula to determine the sum of a series. So before I do that, I'll give you a little historical background. So when Carl Friedrich Gauss was 9 years old, his instructor didn't want to really do anything for a little while. He wanted to grade some papers and not deal with 9-year-old kids. So he put up the following problem on the board. Add up 1 plus 2 plus 3 plus 100. And immediately after he wrote this on the board, Carl Friedrich Gauss goes, "Oh, I figured it out." He jumps up and down and says, "I know what it is. I know what it is. It is 5,050." So let's see how he did this. And so let S equal 1 plus 2 plus 3 plus 100. And now let's write this rather than ascending. Let's do it descending order. So 100 plus 99 plus 98 plus 1. And now let's add these together. And so this is 2s. S plus s is 2s. I get, well, 101 plus 2 plus 99 is 101 plus 3 plus 98 is 101 plus dot dot dot, well, again 101. So each of these are 101. There are 1, 2, 3, 100 of these. And so 2s is 10,100 divided by 2. And so s is equal to 5,050. And so this is one of the one story about him, and he then proceeded to do many things and became very famous for some very difficult problems in mathematics and in statistics. You'll notice. Okay, so let me give you the formula for the sum of the first n terms of an arithmetic series. Okay. So let me call this S sub n. So this is the sum, k equaling 1 to n, of an arithmetic series. Well, arithmetic series, you remember, always has this form, where a sub 1 obviously is a constant, and d is a constant. Well, this will equal well, what he said is, well, let's see. You add the first and last term, multiply by how many terms there are, and then divide by 2. And so you add the first term and the last term. You multiply by how many terms there are, and then divide by 2. That is the formula to find the sum of an arithmetic series. Now, we also have that a sub n, since a sub n is a term in an arithmetic sequence, it's just equal to, well, another a sub 1 plus n minus 1d, just like what we had above. And so we have that it's also equal to this formula. Okay, so let's show this. So I'll show the second formula. It's easier. Obviously, these two formulas are the same, but I'll prove the second one, and I'll do this by induction. So I'll first do the initial case. I wish to show that this formula is true when n is equal to 1. And so I know that S sub 1 is A1, because that's the definition, recursive definition of the partial series. And this is the same as 1/2 times 2 a sub 1. The 2's just cancel. This is the same as 1/2 2 a sub 1 plus 0. Adding 0 to anything doesn't really do anything. So this is equal to 1/2 2a1 plus 1 minus 1 times d. Since 1 minus 1 is 0, 0 times d is just 0. But if I look here, this is just the same as replacing n by 1. So I have here s sub 1, I have 1/2 2a1 plus 1 minus 1d. So therefore, the initial case holds. Let's do the induction case. See if the induction case holds. So first, let's suppose that s sub k is equal to k over 2 times 2a1 plus k minus 1d. And so I just replace n here by k. And so if the kth formula works, let's show that it also holds for k plus 1. Well, by definition, the partial sums definition, I have that S sub k plus 1 is S sub k plus A sub k plus 1. But by the above formula, I have a S sub k is k over 2 times 2a1 plus k minus 1 times d. And by the formula for a sub k plus 1, using the fact that this is a arithmetic sequence, I have that this is equal to a1 plus k plus 1 minus 1 times d. That's the formula for the k plus first term using the general term, the formula for the general term of an arithmetic sequence. So this is equal to, let's multiply k over 2 inside the parentheses. Ooh, no, let's do this first. Let's multiply d. So this is k over 2, 2a1 plus kd minus d plus a1 plus, well, the ones cancel. Well, let's write this, get rid of the parentheses, so it's k plus 1 minus 1 d. The k's will cancel. So I have s sub k plus 1 equals k over 2 times 2a1. Oh, I can actually do that now. Let me multiply k over 2 inside the parentheses. So this is equal to, the 2's cancel, k a1 plus 1 half k squared d minus 1 half kd plus a1 plus kd. S sub k plus 1. So let's add a1. So I have here, combine these ka1 with the a1. So I have a k plus 1 a1 let's combine these two terms. So I have plus 1 half k squared d minus 1 half kd plus 2 1 half kd's give me a plus 1 half kd. And so this is equal to, let's factor out the 1 half k d. So what remains is just k plus 1. Factoring out the 1 half kd. Okay, so now I have s sub k plus 1 is equal to, let me factor out the 1/2 k plus 1. Okay, so what remains is 2a1 plus kd, factoring out the 1/2 k plus 1. So this is equal to k plus 1 over 2a1 plus, let me write k as, oh, maybe I'll do it like this, as k plus 1 minus 1. And lastly, let me group the k plus 1 together. And now I see that this is the exact same formula from above, just replacing n here with k plus 1. So therefore, if I replace n by k, then the formula works when I replace n by k plus 1. Therefore, by the principle of mathematical induction, this formula works for all natural numbers n. And so I'm done. Okay, so let's do some additional problems. Oops. On page 664. Let me find problem number 25. Yep, 25. In exercises 25 through 30, find the sum of the first 100 terms of the arithmetic series whose first few terms are given. So 2 plus 4 plus 6 plus 10 plus 8 plus 10. And you want to add the first 100 terms. Okay, so we'll just use the following formula, that S sub n is equal to, well, actually I had two formulas. I could either use the formula where I add up the first and last term. Do you know the last term? No. Or I could use the other formula, which is n over 2, 2a1 plus n minus 1d. Okay. We know what n is. N is 100. The first term is 2. The common difference, well, we keep adding 2. And so I get 50 times 4 plus 99 times 2. 4 plus 198. So 202. $10,100. So 50 times 202. 10,100. Okay, good. 27. Seven plus 8.5 plus 10 plus 11.5. Okay, so again, let's use, notice that this is an arithmetic series since I keep adding 1.5 to get to the next term. And so S of n is equal to n over 2. I do not know the last term, so I'll use this form, 2a1 plus n minus 1d. So I want to add up the first 100 terms. Oops. The first term is 7. I'm adding up 100 terms. And the common difference is 1.5 or 3 halves. And so 100 divided by 2 is 50. 2 times 7 is 14. 100 minus 1 is 99. So you get 50 times 99 times 3. $297. Okay. Uh, 14. 28 plus 297 is 325. Okay. 50 divided by 2 is 25 times 325. $81.25. And so if you added up all those terms, you get 8,125. 29. $25 plus 21 plus 17 plus 13. So let's add these all up. Again, this is going to be an arithmetic series. We don't know the last term, so we'll use this formula. N over 2, 2a1 plus n minus 1d. Add up the first 100 terms. The first term is 25. We're adding up 100 terms. And to go from one term to the next, you keep subtracting 4. And so this is equal to 100 divided by 2 is 50. 2 times 25 is 50. 100 minus 1 is 99. So we get 50 minus 396. So negative 396. Let's add 50. So you get negative 346 and multiply by 50. So you get negative 17,300. $31. 2, 7, 12 to 102. In exercises 1 through 31, find the sum of the arithmetic series. Okay, so in this case, I know the first and last terms, so I'll use the formula for the sum of arithmetic series where I know the first and last terms. But I don't know how many terms I'm adding up, so I don't know n. So I'm going to have to figure out that first. So let me use the fact that this is the arithmetic sequence. The underlying sequence here is an arithmetic sequence. And let me use the formula for the general term of arithmetic sequence. A sub n is a sub 1 plus n minus 1d. So to find the position of the last term, I'll just let a sub n equal 102. The first term is 2. I don't know n. To go from one term to the next, I keep adding 5. So the common difference is 5. Subtract 2 from both sides of my equation. Divide by 5. Add 1. So n is 21. Okay, so I know that the formula for to find the sum for arithmetic series is the following. That the sum is equal to n over 2 a1 plus an. And so to find the sum of the first 21 terms, you get 21 over 2 times. The first term is what? 2, and the last term is 102. And so this is equal to 104. So 21 times 52 and then multiply that by 21. So the sum is equal to 1,092. Do problem 33. +28 plus 26, 24, down to -6. Again, I'm going to do it the same way I did above, but unfortunately, just like above, I don't know how many terms there are in this in the arithmetic series. So let's use the formula to find the nth term for arithmetic sequence, a1 plus n minus 1d. So to find the position of the last term, I'll just set an equal to -6. The first term is 28. When you go, notice that you're always subtracting 2 to go from 28 to 26 to 24. And so the common difference is -2. Subtract 28 from both sides of your equation. Divide by -2. Add 1 to both sides of your equation. And so there are 18 terms in the sequence. Let me use the following formula to figure out the sum of the first n terms of my arithmetic series. And so to find the sum of the first 18 terms, the first term is 28. The last term is 6. And so 18 divided by 2 is 9. 28 minus 26 is 22. 9 times 22 is 198. So if we add up all those terms, you get 198. Let me do problem number 35. -3, 0, 3, 6. Actually, let me do 34. 1, 3, 5, 7. Exercises 34 through 36. Find a formula for the sum of the first n terms of the arithmetic series whose first few terms are given. And so, let me use the following formula. S sub n is equal to n over 2. I do not know the last term, so I'll use 2a1 plus n minus 1d. The first term is 1. The common difference is 2. Two times 1 is 2. Multiply the 2 inside the parentheses. So you get 2n minus 2. The 2's cancel. So you get n over 2 times 2n. The 2's cancel. And so you get n squared. So you notice that if you add the first n odd terms, you always get n squared. So that's an easy way to figure out what n squared is. You just add up the odd terms. 35. Negative 3, 0, 3, 6, etc. So the sum of the first n terms is just n over 2 times 2a1 plus n minus 1d. And so the sum of the first n terms of this arithmetic series is n over 2 times 2 times a1, which is negative 3, plus n minus 1 times d. The common difference is 3. So S sub n equal n divided by 2 times negative 6. Let me multiply the 3 inside the parentheses, plus 3n minus 3. So S sub n is equal to n halves times 3n minus 9. And that is your answer. 37. S sub 12 is 222. S sub 14 is 301. In exercises 37 through 40, find a formula for S sub n, the sum of the first n terms of an arithmetic series using the given information. And so, I know that S sub n is equal to, well, there's two formulas, but really you don't know the last term. So there's only one formula I can use. So n over 2 2a1 plus n minus 1d. Okay, so let's plug each of these in. So I know S sub 14 is 301. So that's 14 over 2. 2 times A1, don't know A1. But the N here is 14, so I know that. I don't know what the common difference is, D. So I have two unknowns. But that's fine because I have another equation. I know that the sum of the first 12 terms is 222. So I'm adding up 12 terms. I don't know what the first term is. I do know that I'm adding up 12 terms. And I don't know the common ratio. So this says that 7 times 2A1 plus 13D is 301. Well, let's divide by 7. 301 divided by 7 is 43. Call this R1. Similarly, I have 222. Maybe I'll write it the other way. I have 12 divided by 2 is 6. I have 2A1 plus 11D equals 222. So I can divide by 6. So 222 divided by 6 is 37. So I have 2A1 plus 11D is, oops, I forget, 37. Yeah. Okay. So now let's just take R1, subtract from it R2, and so I get 2D equals 6. So D is equal to 3. Let's figure out what A1 is. So from R2, I get 2A1 plus 11 times D is 37. So 2A1 plus 33 2A1 plus 33 is 37. Subtract 33 from both sides. So 2A1 is 4 divided by 2. So A1 is 2. Okay, so find a formula for S sub n. Okay, so let's do that. So S sub n is equal to n over 2, 2A1 plus n minus 1d. So S sub n is equal to n over 2, 2 times a1, which is 2, plus n minus 1 times d, which is 3. So S sub n is equal to n over 2, 4 plus, let me multiply 3 inside the parentheses, 3n minus 3. And so I get that S sub n is equal to n over 2 times 3n plus 1. And that is the formula for the sum of the first n terms. Let me do problem number 39. A1 is 5. The sum of the first 18 terms is 589. I know that S sub n is n over 2 times 2a1 plus n minus 1d. Therefore, the sum of the first 18 terms is 589, and I'm adding up 18 terms whose first term is 5, and I'm adding up 18 of them. I don't know the common difference yet. And so 589 is equal to 9 times 10 plus 17d. So 589 is equal to multiplying 9 inside the parentheses. 90, actually, yeah, let's not do that. Is equal to 90 plus 17d. Subtract 90 from both sides of your equation. Ooh. Nine times 17 is 153. Subtract 90 from both sides of your equation. Divide both sides of your equation by 153. That's 18. That's 22. So D is equal to 499. Let me just see something. Okay. Yeah. Okay, it's around 3. And so, I have that S sub n is equal to n over 2. That's 39 times 2a1 plus n minus 1d. So S sub n is equal to n over 2, 2 times a1, which is 5, plus n minus 1 times d, which is 499 over 153. Nothing's going to make it look much better than that. I guess I'll multiply it out, but okay, so this is equal to n over 2, 10 plus okay. So let's get a common denominator at least. So 1530 is 1031. And so you get that S sub n is equal to n times 499n plus 1031 over 306. Okay. Okay, so let me do 41. Let me check something. Let's see. This is problem number 39. In section, what is this? $15.5. $39. What? Okay, 1 second. 15.5. Oh, I wrote it wrong. Okay. 549. Which makes everything much easier. Okay, that's 9 each. Oh, it's divisible. Okay, so the sum should be 549. So that'll make that formula just much easier. Okay. Okay, so do problem 39. The first term is 5, so a sub 1 is 5. The sum of the first 18 terms is 549. So let's plug in 18 to the formula. And so I have 549 is equal to 9 times 10 plus 17d. Let's divide both sides of my equation by 9. That's divisible by 9. 549 divided by 9 is 61. And that's divisible by 17. Subtract 10 from both sides. So 51 equals 17d. Divide by 17. So d is equal to 3. And so my formula for the sum of the first n terms, S sub n equals n over 2, 2a1 plus n minus 1d gives us n over 2 times 2 times the first term, which was 5, plus n minus 1 times d, which we calculated as 3. Multiply 3 inside the parentheses. And so S sub n is equal to n over 2. 2 times 5 is 10, plus 3n minus 3. And so you get that S sub n is equal to n over 2 times 3n. 10 minus 3 is 7. And that's your answer. Okay, let me do problem 41. Sum k equaling 1 to n of 2k is equal to n times n plus 1. In exercises 41 through 46, use mathematical induction to prove the following identities. Okay, so let's do that. So let's first do the initial case. So I want to show that this formula is true when n is equal to 1. So let's 1 times 1 plus 1 is equal to 2. Okay. Actually, maybe I'll just leave that. The sum k equaling 1 to n, I'm assuming here that n is going to equal 1 for the initial case, of 2k is equal to, well, 2 times 1, which is 2, which is the same as 1 times 2, which is the same as 1 times 1 plus 1. So I've shown that this formula works when we replace n here by 1. Okay, so the initial case holds. Let's do the induction case. Let's suppose that this is true for, oh, maybe capital N, where k equaling 1 to, let's say m. Let's do m. Okay, so let's suppose that the sum k equaling 1 to m of 2k is equal to m times m plus 1. Okay. So then I have that the sum k equaling 1 to m plus 1 of 2k is the same as, well, the sum of the first k elements plus the very last one, which is found by just replacing k by m plus 1. But I know that these first few elements, the first m elements, let me write this down. By the above formula, the sum of the first m elements is just m times m plus 1. I can actually factor out m plus 1. So what remains is m plus 2. And let me write m plus 2 as m plus 1 plus 1. And so I've shown that this formula here works when we replace n by m plus 1. So if I just plugged in m plus 1, well, it's the same formula. Therefore, the induction case holds. So, therefore, by the principle of mathematical induction, this formula, sum k equaling 1 to n of 2k, is just n plus 1, and this is true for all natural numbers n. And that's what you wanted to show. Let's do problem number 43. I want to show that the sum k equal 1 to n of 4k minus 1 is just n to n plus 1. Okay, so let's do the initial case. So again, I'm going to prove this by mathematical induction. Let's do the initial case. The sum k equaling 1 to 1 of 4k minus 1 is just 4 times 1 minus 1. Well, 4 minus 1 is 3. But I can write 3 as 1 times 3. And I can write 3 as 2 plus 1, which is 2 times 1 plus 1. But this then says that the formula works when I replace n here by 1. And so I've shown the initial case. Let's do the induction case. So suppose that this formula works. For the first m natural numbers. Okay. Then let's look at the sum, calculating 1 to m plus 1 is equal to the sum of the first m elements plus the last one. By the induction hypothesis, the sum of the first m is just m, 2m plus 1, plus, let's multiply this out. So this is 4m plus 4 minus 1. Multiply the m inside the parentheses. So this is equal to 2m squared plus m plus 4m plus 3. So I get 2m squared plus 5m plus 3, which is 2. Let's do the other way around. M plus, no, maybe it is that way. Let's do 2m plus 1, m plus 3. Let's see, how do I want to write my answer? Oh, I want to write the other way around because I want the 2 on the other side. So let's write this as m plus 3, 2m plus 1. Okay. Oops. Of course, I wrote it the wrong way now. So this is 2m squared plus 3m plus 2m is 5m plus 3. So now I can write this. So this was the sum equal 1 to m plus 1 of 4k minus 1 is equal to m plus 1 times 2m plus 2 plus 1. And so I can write 2m plus 3 as 2m plus 2 plus 1. But notice that this formula is the same as this formula, where I've replaced n by m plus 1. And so I've shown that the induction case holds. So therefore, by the principle of mathematical induction, we have that the formula, the sum k equaling 1 to n of 4k minus 1, that this is equal to n times 2n plus 1, and this is for all natural numbers n. And that's what you wanted to show. Let me do problem number 45. Sum k equaling 1 to n of 10k minus 6. Show that that's equal to n times 5n minus 1. Okay, so let's prove this by induction. So let's do the initial case first. Let's find the sum, k equaling 1 to 1 of 10k minus 6. So this is just 10 times 1 minus 6, which is 10 minus 6, which is 4. I can write 4 as 1 times 4, which is 5 minus 1, but 5 times 1 is also 5. And so I have that the sum, k equaling 1 to 1 of 10k minus 6, satisfies the formula. So if I replace n here by 1, the formula worked. Ah, yes. I'm sorry. The formula, I was like, wait, that didn't work. I did the wrong thing. So if we replace n here by 1, then I'm shown that the formula worked. Okay. So now let's do the induction case. Let's suppose the sum k equaling 1 to m of 10k minus 6 is equal to m times 5m minus 1. Then the sum of the first m plus 1 is equal to the sum of the first m plus the last term, which is 10 m plus 1 minus 6. Okay. Well, by the induction hypothesis, the sum of the first m terms is just m times 5m minus 1. Multiply the 10 inside the parentheses. So this is 10m plus 10 minus 6. Multiply the m inside the parentheses. So this is 5m squared minus m plus 10m plus 4. So this is equal to 5m squared plus 9m plus 4. And so let me factor this. This factors as m plus 1 times 5m plus 4. So you get 5m squared plus 4m plus 5m is 9m plus 4. So this is equal to, let me write this down, the sum k equal 1 to m plus 1 m plus 1 And this is the same as I can write 4 as 5 minus 1, and I can write 5m plus 5 is 5 times the quantity m plus 1. And now I notice that if I replace n by m plus 1, this formula works. And so I've shown the induction the induction case holds. So therefore, by the principle of mathematical induction, this formula works for every natural number n. And that's what I wanted to show. Let me do problem number 47. Use mathematical induction to show that for every natural number k sub 0 and for every natural number n bigger than k sub 0, we have the following. The sum k from k0 to n of a sub k plus the sum k equaling k sub 0 to n of bk is equal to the sum k equaling k0 to the n of a sub k plus b sub k. Okay, so let's show that. So let's do the initial case. So I have the sum k equaling k sub 0 to k sub 0 of a sub k plus sum k equaling k sub 0 to k sub 0 of b sub k. This is just equal to a sub k 0 plus b sub k 0, which is the sum k equaling k sub 0 to k sub 0 of a sub k plus b sub k. And so I've shown that the above formula holds when n is equal to k sub 0. So let's do the induction step. So let's suppose that this holds for m, for some natural number m, obviously bigger than k sub 0. I want to show that this works for the m plus first case. Okay, so the sum k equaling k0 m plus 1 sum k equaling k sub 0 m plus 1 bk is equal to the sum k equaling k sub 0 to m a sub k plus the next term a sub n plus 1 plus, let's do it for the b's, sum k equaling k sub 0 to m bk plus b sub m plus 1. So this is equal to by the assumption above. Oh, well, let me do commutative property. So this is equal to. So the sum. So by the commutative property of addition, I have the following. Plus your a sub m plus 1 plus b sub m plus 1 by the commutative property. For addition. But this is equal to, by the induction hypothesis, the sum k equaling k sub 0 to m of ak plus bk. And so I've shown that the sum of these summations well, this right-hand side is just the sum k equaling k sub 0 to m plus 1 of ak plus bk, just by the definition of the summation. And so I've shown that the induction the induction case works, and so therefore by the principle of mathematical induction, that the sum k equaling k sub 0 to n a sub k plus sum k equaling k sub 0 to n b sub k is just the sum k equaling k sub 0 to n of a sub k plus b sub k. That this is true for all natural numbers n. And so I'm done. And so that finishes off section 15.5. And I will see you on Monday.